Hi there and welcome to this video for Senior Physics on Electromagnetism and Electricity. In this video we're going to explore the characteristics of a PN junction diode and some of the uses of these diodes. Now basically the characteristics for a diode can be set up using the circuit that you can see opposite. Now what we've got here is a PD which is basically controlled using a variable resistor. That's the resistor with the arrow, the first one on the left hand side. That then flows through a diode where a voltmeter is attached in parallel across it. Then it flows through a resistor and then a current is basically measured using a milliammeter. Then it goes back to the power supply. So basically we know that diodes are non-ohmic. Remember, if you're ohmic, then V over I will produce a straight line, where the gradient of the straight line will be the resistance. Now with it being non-ohmic, what happens is diodes and semiconductors basically work on the principle that as you increase the temperature, you increase the number of free electrons which are available within the semiconductor. As a result, that's allowing more current to flow. So more electrons produced by more heat means less resistance, and the result is you get a curve which is going to be generated. So we know that they're not ohmic. We know that it can be constructed using the diagram that we've got opposite, and what we get is a curve which you can see below. Now the key thing to understand is if we look at a diode working normally, we're looking at the right hand side of the graph. So basically in the positive quadrant for X and Y. And you will notice that where the blue circle is, this is the diode working in the forward bias. Now if we track down from that vertical line, you can see it crosses the x-axis around about between 0.5 and round about 0.7 volts. Now if you remember back to what we were talking about, 0.7 volts is 0.7 joules per coulomb. That's the amount of energy that is required for the electrons in the n-type conductor to flow into the p-type conductor, into those holes, and basically have enough energy to jump over that depletion zone. So as soon as you're able to jump over that depletion zone, then you've got current flowing, there's no problem. There is no increase in voltage. You only need that 0.7 joules of energy, and then that's it. All electrons will clear that depletion zone regardless if we put more volts into the system. So this is known as the forward bias, okay, because it's working in the forward direction. Now you will notice that, as I say, it never gets higher, the voltage never gets higher than 0.7 volts. But in the reverse bias, as denoted by the yellow, you will notice that it takes a huge amount of voltage before you get a drop in current. And notice the current, where it says reverse current at the bottom of the y-axis. This is measured not in milliamps, but in microamps. So you'll get a small flow of current going backwards, but at a very high voltage. Now, if we put too high a voltage on there, what will happen is the whole thing will break down and the diode will stop working. So that's basically what's happening in a reverse bias situation. So it prevents the current flowing through at high voltages, and the result is you're going to protect the system. The key thing as students is that often in an exam you might be given one of these curves and expected to read into it the idea of forward bias, i.e. you read the curve on the right hand side, or reverse bias where you're working on the left hand side of the graph. And it's important that you understand those two concepts. As I say, it's going to make life easier when you read the question. You're looking for forward bias or reverse bias, and that tells you where to look on the graph. Once you're able to look on the graph, the result is you can work out various voltages, etc., etc., and then you can be asked questions accordingly. So that basically runs through the current and voltage characteristics for a diode. Now what we're going to do is look at, well, what are the uses of these diodes? Now one of the uses of a diode is something like an LED. Now you can see LEDs here. LEDs now are used a huge amount for indicator lights, but you'll also find that LEDs are now being put into light bulbs, and they are a very efficient way of generating light because they do not produce any excess heat. the old halogen light bulbs used to, but now you can get light bulbs which are all LED related. There's no energy loss through heat, which makes life very easy. But how do they work? Well, basically, they work by the electrons giving up their energy in the form of a wavelength of light when they basically combine with the holes in our semiconductor. As a result, different wavelengths of light can be generated, and as a result of that, we get different colors which are being produced. So that's an LED, which is a light emitting diode. Basically, it's got the symbol for a diode with two arrows coming off it. And you can see some examples of LEDs, which is shown here. Key thing to note about an LED, it's a diode, which means that you have to get it going in the correct direction. So when you load up your diode, you're going to have to make sure that your arrow and your line is going in the right direction with the current, otherwise it won't work for the reason that we talked about earlier when we looked at diodes. Another use of a diode is a Zener diode. Now a Zener diode is a very interesting diode because it works in reverse bias. If it's working in reverse bias, you need to look at the left-hand side of the curve. So you can see the IV characteristic curve down in the bottom right-hand corner. Remember, you're going to be looking at the left-hand side of that curve, anything to the left of the y-axis. Forward current you're not interested in because Zener works in the opposite direction. So as it says here, it can conduct up to, from anything from 2 volts up to several hundred volts, depending on the type of Zener diode it produces. And what it then basically works on is anything above that with respect to voltage has no effect on the circuit. Current will still flow at the same amount, current will increase, but you'll get no increase in voltage, which means that you can control the amount of voltage which is going through the circuit, because you're not going to get any more which is going to have an effect. You'll only get a certain amount of voltage which is going to control that circuit, and as a result it makes it a very, very good voltage regulator. So Zener diodes, you can see the symbol shown in that second diagram. They work in reverse bias, meaning that you've got to look at the left-hand side of the y-axis if you've got an IV characteristic curve. Okay, another thing that we can have is a thermistor. You can see the symbol here. Basically, this is a diode that works working on indicating temperature, and it looks at the electric current, which is basically working on with respect to temperature. And finally, we've got an LDR, or a photocell. Again, the symbol shown on the right hand side. This will react depending on the amount of light that you've got present. For example, if you use solar cells in your garden, they will switch on when the light goes down, and that will all be generated by a photocell. So it'll either switch on or switch off the circuit depending on the amount of light which is actually generated. Again, it's a diode, and as a result, it has to go in a specific direction. So this is just a few uses of how we can use diodes. I hope you found that useful. Join me again for our next video, where we're going to combine everything together and look at how we convert AC to DC using our diodes and our capacitors, which will round off this topic of electronics. Okay, well, thanks for watching, and I look forward to you joining me again.